Yeah. Hi, everyone. Today we have Vitaly as our speaker. He's a research scientist at Apple AI Research. He's going to talk about his work hiding the model clones, a simple and nearly optimal analysis of privacy amplification by shuffling. Yeah, let's welcome him.
Can you hear me?
Yeah.
Thank you for inviting me. It's a great pleasure to speak at your seminar. It's not going to be a talk about crypto, but it will hopefully be of some interest to anybody interested in crypto. So this is joint work with Audra Macmillan and Kunal Talwar, who are also in the same group with me at Apple. And it is based on two papers. One is already published, and another one is currently in review and will appear on arXiv soon. Please, by the way, since I imagine some of the things will be not as familiar to you as they are to people working in privacy, please feel free to stop and ask questions. If I don't see I probably won't see most of you, so just interrupt as I speak. There is no problem at all. Anyway, let's get started. So the main motivation for this work is private federated data analysis, and this is broadly a setting in which we have a number of clients, such as user phones, holding some important piece of data. And we have a server that wishes to perform some kind of data analysis on that data, such as building a histogram.
Sorry, I think that you're in presentation mode, but we're only seeing like the standard keynote view with like the slides on the left and then just the title slide.
That's strange. Okay, so just the title slide. Okay. Let me try to either change the share.
Yeah, you might need to share the presenter view.
Okay, there is a resume share button. Does that do anything? Do you?
Not really doing anything.
Maybe let me try the new share. I'll do the whole desktop.
Adding the mirror mode.
Okay, let me try the whole desktop. That might hopefully will be better.
If you share the full screen, definitely that.
Yeah. View, then maybe play. I'll stop the play and I'll now do full screen and then play. Okay.
Yeah, that's perfect. Yeah.
And maybe just to move now it's not showing I just need to hide the floating. Okay, that should be fine. Okay. So we are now on my controls are okay. They do work. So as I mentioned, we're doing private federated data analysis. We have a server that wishes to analyze data held by users, where we think of each user as holding a single data point, say x1 through xn. And the typical data analysis we are interested in are building histograms, training machine learning models, and so on and so forth. As we all know, much of this user data is sensitive. It could be health records, financial records, even just messages. So users are understandably concerned with sharing this data, their data with the server, and we need to provide some kind of ideally some kind of guarantees of privacy to the users. And now, sort of the method which has been accepted by the academia and deployed in industry is based on the notion of differentially private local randomizers, in which each client will run an epsilon differentially private algorithm on their data. This notion has a kind of pretty interesting history. A special case of it has been developed back in '65 in social sciences to kind of give users who participate in surveys some notion of privacy. It has then been discovered or proposed in database community by Efimevsky et al. And somewhat more recently, it has been realized that this is a special case of the notion of differential privacy by Dwork and others. More formally, this notion it has the following definition. It says that an algorithm is an epsilon differential private local randomizers if for any two possible inputs in the domain of that randomizer and any possible output value, the probability of that output value under the first input, the ratio of these probabilities of outputting some specific value y is upper bounded by e to the epsilon. And okay, informally, it looks something like this. The ratio of the densities is always upper bounded by this e to the epsilon, where epsilon is what measures the privacy. Informally, you can think of it as basically this epsilon measures our ability to distinguish between these two possible inputs of the users based on an observation y. So that's a very nice guarantee. Unfortunately, it is not it has a price. For example, if we look at the best error that is achievable for the very simple data analysis task, such as a mean estimation of values between 0 and 1. Again, we think of each user as having just a value between 0 and 1, and we want to estimate the mean of these values. Then the best value we can achieve while ensuring this epsilon local differential privacy is on the order of 1 over epsilon times square root of n, which is not great. 1 over square root of n is already not great. And in addition, we even multiply it by epsilon. And more importantly, we know that if the only thing we cared about is ensuring privacy, and we had a trusted server, so we know that we could provide this kind of central notion of differential privacy with error which scales as 1 over epsilon n, which is 1 over square root of n, basically a square root n better than the error we get in the local model. And it's a significant difference. And in case you, I don't know, not familiar or forgot what the central notion of differential privacy is, here is the definition by Dwork and others. The algorithm is said to be epsilon, and often we allow slight kind of error delta differentially private algorithm if for any pair of data sets that differ in a single element and any basically event or set of outcomes z in the output space, the probability of that event under the first data set and the ratio to the other data set is at most e to the epsilon up to this delta. We allow this delta correction. And it's a standard notion. And maybe the way to think about the difference between these two notions is that in the local model of differential privacy, we guarantee differential privacy when we observe everything that is being communicated by the user. Whereas in the central notion, we only guarantee it under the observation of the output of the algorithm, which could be just the mean or some other computation that the algorithm performs. So as I mentioned, the price is not, there is a price for this local model. And as a result, in most deployments, in order to achieve reasonable utility, one has to use a relatively large epsilon, which is larger than 1, which is undesirable. Especially we know that above 1, the privacy scales as e to the epsilon. So it's actually exponential ratio in between these probabilities. So effectively, the privacy guarantees become weaker since the server can now gain this non-trivial amount of information about the user. And to address this kind of limitations or these concerns, privacy concerns with the use of epsilon being larger than 1, Vitaly et al. Proposed the following solution. They proposed introducing a shuffler as an intermediate step between the server and the client. So basically, the shuffler will collect all the reports from the clients, will shuffle them completely randomly and uniformly, and then give the shuffled responses to the server while kind of removing any sort of metadata or any time steps, anything that could potentially identify the user, or leaving only the reports on the data. So In this model, if we assume that shuffler and server do not collude, they belong to different entity, otherwise, of course, there is no point in this, then we can say that in addition to getting reports that have been randomized, the server doesn't even know whom each report comes from, and it seems like it should provide some additional privacy guarantees because they are randomized. And we also don't need to trust the shuffler because all this shuffling can be done on an encrypted reports. So shuffler, again, doesn't learn anything about the data, and we don't need any privacy assumptions.
Sorry, but I guess you need to assume that the shuffler does indeed shuffle at random, even if it doesn't see the values.
Right. Yes, we need to assume that the shuffler does its well, of course, to get anything useful out of it, we need to assume that shuffler actually does what it promises to do. Right, and that, of course, there is a natural question of how do we certify it in some way or verify, but that's sort of we will not be talking about this part. We're primarily trying to understand. So this does look like this should be providing some kind of additional privacy benefits, but the problem is the question is, can this be formalized? Can we say something formal about these improved privacy guarantees? And specifically, this is the question of privacy amplification. Does privacy amplification happen here? And where we formulate the problem as a problem in which we think of each user as reporting sending their data with some initial epsilon 0. Then this data being shuffled, and the server gets to observe the shuffled data. And the question is, what kind of privacy guarantees can we prove about the data after shuffling? So if we look at this output, does it satisfy better differential privacy guarantees than the original epsilon 0? So we always get the same epsilon 0 just because everything is close to post-processing, but can we get something better? And maybe I should mention that this question of privacy amplification, if one can establish that shuffling amplifies privacy, one also will get that any other kind of symmetric functionality, something that will provide the same better privacy guarantee. For example, if instead of shuffling, we'll do aggregation, naturally aggregation does not, such as addition, or because it is also order independent, it will satisfy the same improved privacy guarantees. So, so this is the question, and it has been formally addressed in two concurrent work. The first one by Chu Smith and others has analyzed specifically the binary randomized response, which is kind of maybe the most basic local randomizer just for binary values. And I'll describe if you're not familiar, I'll describe it later in the talk. But for now, it's maybe the most basic mechanism, just outputs randomizes between the two values 0 and 1. And for this particular mechanism, they have proved that after shuffling, the algorithm will satisfy the privacy guarantees which are given in this formula. And it might look a little complicated, but ignoring the sort of less important terms and looking only at, we can look at the two regimes, the regime in which epsilon 0 is less than 1. And in this regime, we get roughly square root n amplification for privacy, which is, again, very significant amplification and kind of effectively gives us back that square root n factor that we lost when going from central model to local. Basically gives us that factor back, gives us essentially the same trade-off as if we were operating in the central model. For epsilons that are larger than 1, and as I mentioned, this is the important regime, the amplification works a little differently. It switches to this regime where it amplifies from e to the epsilon 0 over 2, but amplifies that value by square root of n. Although this is, again, the correct behavior that for many problems allows one to get back to the same trade-off as one gets in the central model of differential privacy. And it's also easy to show that this is the tight, these bounds on the privacy are asymptotically tight. one cannot hope to get anything better. In this case, again, it's very easy to analyze this particular randomized particular randomizer. So in the other work, by Erlingsson.
I have a question actually. So the first regime is the most important regime when epsilon 0 is less than or equal to 1.
No, it's actually the other way around. Yeah, in general, for central privacy, we would want the final epsilon to be less than 1. But with local privacy, we know that we cannot hope to do much with epsilon 0 less than 1. Just the errors end up being too high. So almost always one needs to use epsilon 0s, which is larger than 1. And in a way, this kind of shuffling is what gives it it kind of justifies this use. By itself, it's not a great guarantee, but once you shuffle it, you do end up with, after this amplification, you do get to epsilons which are less than 1. So let's say
so epsilon 0 is the local privacy parameter used by each user.
Yes. That one can be like large, and it's not very large. It's maybe like 5 or 6 or 4. But once you amplify it by the square root of n, okay, we first exponentiate it, but then by e to the epsilon over 2, and then you divide by square root of n, it can bring it down to below 1 for reasonable values of again epsilon 0 and n. And that's sort of as we'll discuss this the specific exponent that we'll be getting, this e to the epsilon instead of e to the that one gets in the regime when epsilon 0 is larger than 1, is basically the main topic of this talk. So maybe let me mention that in a concurrent work by Erlingsson and others, including myself and Kunal, who is also on this paper, we gave a general privacy application via shuffling, and I'll describe in which sense it is general, but basically it applies to all randomizers and also more general settings, which gives a bound which has the same behavior has same optimal behavior when epsilon 0 is less than 1, but when epsilon 0 is larger than 1, the bound is e to the 3 epsilon 0 divided by square root of n. And again, it's a big difference, just maybe substituting something like epsilon 0 being equal to 4. It suddenly makes sort of the bounds that one get one would require much larger n to get to bring it down to below 1. So this is the the bounds are in the second result, in the more general results are worse. So the first one is simple and tight, and the second one is not only not tight, it's also actually pretty complicated. It's unfortunately not a simple proof. I mean, it's not very complicated, but it's quite subtle. And the hope in this work is actually to address this gap. But let me first tell you a little bit more about what is a general privacy implication via shuffling states a little more formally. And here is the formal statement of the theorem that proved in that paper that I mentioned. And it says the following for any adaptive sequence of local randomizers A1 through AN. And what do I mean here by adaptive is that actually I allow A2 to observe the output from A1 and A3 to observe all the previous outputs and kind of modify their behavior on the basis of these previous randomizers. And this adaptivity is actually very important in machine learning. As we, for example, train a machine learning model, we need to compute gradients at different points. So the randomizers, which need to randomize the gradient, kind of end up depending on the point we're computing it for. So they basically, need to be adaptive. This is not a fixed set of randomizers. They first need to compute the gradient and then only then randomize. So for any sequence, adaptive sequence, in any data set, which we denote by x1 through xn, we denote by A with the subscript shuffle of this data set to be the algorithm that behaves in the following way. It first picks a random permutation of the data, permutes randomly the data, and then applies the randomizers in the same sequence, but to this permuted data. Then this algorithm applied to the permuted data satisfies the differential privacy guarantees of this stated in this bound. For some reason, pointer doesn't work for me, so I hope you can just guess what I'm talking about. And again, if needed, feel free to stop me. So this maybe I should mention two things about this result. First, it may be a little bit confusing because here I'm shuffling the data and applying the randomizers to the data, but whereas in the motivation we were actually first applying the randomizers and then shuffling the reports. But in the motivation that I've described, the way it was stated, the randomizers are identical, at least typically is applied to identical randomizers. And in this case, it doesn't matter whether you shuffle before or after. For identical randomizers, it doesn't matter whether you shuffle the data before or after applying the randomization. But this ability to deal with randomizers which are chosen adaptively allows one to use this privacy amplification for analysis of algorithms like differentially private SGD. So maybe the point is of this general results, it can be then applied in other settings, not just directly for analysis of this privacy amplification in the federated setting. It can be applied in other settings and allows to analyze other algorithms as well. So that's the general result, and there has been quite a bit of follow-up work on trying to improve this type of results. So the first follow-up work was by Bal and others, who showed that if one, at least for non-adaptive case, one can improve the exponent from 3 epsilon 0 to just 1 epsilon 0, still worse than epsilon 0 over 2, which we want in the optimal result. And the Bal and others in a different work have sharpened the general result from the constant of 3 to a constant of 2.5. We have somewhat very similar technique to the previous result. And they have also observed that it can be applied to the case when local randomizers have this slightly weaker epsilon 0 delta 0 local differential privacy. Although the asymptotic result in this case is really bad. It's e to the 20 epsilon 0, making it not useful in practice. So this is the prior work, which in addition to not being tight, is also quite involved to understand. Which brings me to our work, and the main result is that we prove this general privacy amplification via shuffling now with this asymptotically tight constant on the whatever e to the epsilon 0 over 2. Again, for the regime where epsilon 0 is larger than 1, it's tight. In the regime where it's less than 1, it has been tight even in the initial result. And again, in addition to being tight, it's a relatively simple result. I'll try to give you some intuition about it later. It also has quite a few other advantages. So first of all, kind of in addition to this general statement, we have a way to exploit this additional structure in the randomizer to get even better bounds. And we can apply that, for example, for a k-ary randomized response, we get actually asymptotically better bounds. We extended to approximate differential privacy without paying almost any penalty. So it's with the same e to the epsilon 0 over 2 exponent. And maybe from the practical standpoint, the most important advantage is that it's relatively easy to compute numerically. In a way, the main result can be seen as a reduction of this general bound to a divergence between two explicit distributions over 3 values. And because that distribution the divergence can be computed numerically, we get a way to get general bounds on the privacy amplification. So let me tell you a little bit about the specific numerical results we get, and this is a little bit somewhat busy plot, but let's first start that we are mapping. We're looking at the plot of how does epsilon 0 map to epsilon, which is the y-axis, after the amplification for specific setting of n being equal 1,000,000 and delta being equal to 1/1,000,000. And the green line, which is the lowest, is the lower bound, which is basically the amplification one gets specifically for the binary randomized response. And for this one, we can compute numerically what's the best like specific divergence, the privacy guarantees. And this is basically something that one cannot improve upon. It's numerically computed lower bound. Our result is this purple line clones, which is numerically computed. And it's, as you can see, it's most within a factor of about 1.5 of the lower bound. Then there are several bounds, some of which are the dashed ones are closed form expressions, so they're in a way a little nicer, and the non-dashed one is the blue line, is basically the best numerically computed bound. As you can see, they're all at least an order of magnitude worse, except for the binary randomized response closed form, which is maybe a little better, but it's again, it applies only to the binary randomized response. So that's the summary of numerical improvements. Let me now talk a little bit about how we prove this result, just to give you the intuition behind the sort of the main idea that we introduced to the analysis of privacy amplification. But before going there, let me basically describe you how one would analyze specifically the binary randomized response. It's extremely simple randomizer, and in fact its analysis has been done before because it reduces to analysis of divergence between two explicit distributions, but we'll do it a little bit differently, not the same way, just to kind of illustrate the ideas that we're trying to do. So first of all, what is the binary randomized response? It's a randomizer which gets as an input a binary value, Boolean value, is a 0 or 1, and it outputs the correct, well, the value that it have received with probability e to the epsilon 0 over e to the epsilon plus 1, and the negation of that value with probability 1 over e to the epsilon plus 1. And it's easy to see that it's e to the epsilon 0 private. And again, because it outputs either 0 or 1 and then permutes randomly the outputs, it's easy to see that basically the distribution of the outputs is fully determined by the number of say ones in the output because of the symmetry. So to analyze it, we'll first kind of we'll look at this kind of equivalent but slightly different way to define this randomizer in the following way, as with probability e to the epsilon minus 1 divided e to the epsilon plus 1, this randomizer outputs the truth, its true value, and probability 2 to the e to the epsilon minus 1, it outputs a random coin flip, random unbiased coin flip, which is this Bernoulli with 0.5. That's again an equivalent definition. Now, using this equivalent definition, let's analyze the privacy amplification for this mechanism. And for this, let's us look at two data sets, X and X prime. And we'll, for simplicity, assume that the first element in the first data set is 0, and the first element in the second data set is 1. And there is that's without loss of generality. Now, as I mentioned, the number of ones in the output distribution fully determines the output distribution. Basically, the distribution of the number of ones is it's sufficient to understand the distribution. And it is not hard to see that the number of 1 in the output distribution can be generated as follows. First, we'll pick some number of C from the binomial distribution. So maybe let me make a quick step back. The way we'll be thinking of this two data set as the first element being sort of the unique one, which we're trying to distinguish. We're trying to distinguish what is the value of x1 and x1 prime. And we'll think of all the other elements as being this kind of crowd that generates, which tries to basically, by throwing in some kind of noise or by allowing these two elements the responses from these two elements to hide in the responses of the other ones, the crowd, the other n-1 elements, we'll be looking at how these elements are contributing to the privacy of the first element. So the way we'll analyze it will first, we know that according to the definition of this binary randomized response, each of the elements with probability 2 over this e to the epsilon plus 1 will output a random coin flip. So we first sample C from the distribution of the number of coin flips in the crowd. So there are n-1 elements in the crowd. Each generates a coin flip. Each will generate the probability coin flip with probability 2 over e to the epsilon plus 1. So the total number of those who will generate the coin flip is binomial with this bias and this number. Now, among those which we have chosen to generate the coin flip, the number of coin flips which turn out to be 1, the number of people in the crowd which will report 1, will be distributed as A, which is again binomial with the number is C, and the bias is half. And now for the all elements, for all the other elements that chose to report their true values instead of a random coin flip, we'll denote by T the number of ones, because they report their correct values, then the number of those which report 1 in the crowd will be denoted by T. Now, having sampled these variables, we can see that the distribution of ones, when we apply, when we shuffle the reports, is distributed as follows. The first element will report 1 with probability, whatever this Bernoulli will randomize the 0. So we'll output 1 with this 1 over e to the epsilon plus 1. It will then add all the ones from those who flipped from the A ones, which returned 1, and those who were flipping random coin, unbiased coin, plus those which reported 1 because they reported their value truthfully, and that value was 1. And at the same time, if we look at the distribution of ones on the data set X prime, it's the same distribution except the first user, because they are reporting 1, the first output will be this Bernoulli e to the epsilon 0 plus e to the epsilon 0 plus 1. And sort of the important part in this way to look at this distribution is that both of these terms has this plus A term, which is basically distributed, and A is the binomial, basically a binomial noise. It's a binomial distribution, and one way to think about it as an addition of binomial noise with expectation C, where the expectation C is roughly n over e to the epsilon 0. This is roughly the number of users that will be outputting the random coins, random unbiased coins. So now we basically see that there is some report, which is itself already noisy, plus we add some binomial noise to it. And we kind of understand that, first of all, it's known that addition of noise is the kind of a standard way to ensure differential privacy. And specifically binomial noises behaves roughly like as a Gaussian of the same variance. It's a little less clean, but it's quite similar. So basically, if we two binomial distributions, this binomial addition of binomial noise, the divergence between the binomial noise and binomial noise shifted by 1 has this divergence, which is in terms of differential privacy, it will have this correct dependence e to the epsilon over 2 divided by square root of n. Of course, it's some logarithmic factor. In addition, because we know that the first element reports the true value also only with probability e to the epsilon minus 1 times e to the epsilon plus 1, we get some additional amplification of by the factor of 1 minus e to the epsilon 1, which is kind of covers that regime when epsilon 0 is less than 1. And together, these imply that the randomized response has the privacy guarantees that that we claimed. Again, it shouldn't be very impressive because, again, this is a very simple to analyze algorithm. But what we'll now show that at least at high level, this is something very similar happens with general randomizers as well. And to see this, we'll first recall the definition of epsilon local randomizer. By the way, so far, I hope everybody's still there and makes sense.
There's a question in the chat from Mingxin.
Oh, I can see the chat. If anybody could read to me.
So in the previous page, I think there is one expression that is a little bit incorrect.
Okay, sure. Please let me know. Yes, e to the minus epsilon 0. Yeah. You're right. Yeah, it should be 1 minus e to the minus epsilon 0. Thanks for pointing out. It's in the term below it. It's written correctly. Yes, there is a typo. Thank you. Or did you mean, unless you meant something else?
Yeah, thank you. Yeah, that's exactly.
Yes. Okay. So recall the definition of local randomizers, where we know that for any 2 possible inputs and any output, the ratio that for any 2 of that of the probability of that output is at least 1 over e to the epsilon 0, because it is at most the opposite of the ratio is at most e to the epsilon 0. And what that sort of immediately implies is that basically, if you look at the density of every element, at least 1 over e to the epsilon fraction of that density can be kind of attributed to the other elements. So basically, maybe one way to think about it is that you can think of output of the randomizer run on X prime as outputting the same output as A being run on X with probability 1 over e to the epsilon. Basically, we are dedicating that fraction of the total output probability to A of X, and with probability some 1 minus 1 over e to the epsilon 0, it will output some kind of leftover, whatever is left over from the after you subtract the other element. So basically, we can think of any element as pretending to be a randomizer on any element as pretending to be randomizer on a different element with probability 1 over e to the epsilon 0. And that's what we'll refer to by cloning. We'll take an extra step, basically just applying the same argument twice. We can, and applying it maybe specifically to x1 and x1 prime, the elements, the first element, the 2 different first elements, and any xi from the crowd. We can think of the output of xi from the crowd as pretending to be the first element in the first data set with probably 1 over 2 to the epsilon 0. We just dedicate that much of the density as pretending to be the first element output of the same randomizer of the first element in the second data set with probability 1 over same probability, or being some kind of leftover probability. So any element in the crowd can pretend to be with probability 1 over epsilon 0, will with probability half behave like the element from the first data set, and with probability other half as the first element from the other data set. So every element from the crowd will be generating a clone of either the first or the second element randomly. And the total number of clones is roughly, again, will be n over e to the epsilon 0. So that's and because the number of clones will be random binomial, we'll essentially get exactly the same or very similar behavior. The constants slightly change from the binomial case, but asymptotically they're even the same. So we will get essentially the same analysis. And at the end of this analysis, again, it's a little more subtle in the adaptive case, but not that much more difficult. We'll get the following theorem that again, the beginning starts as the same as in the general result that I mentioned before. We have this adaptive sequence of local randomizers, which we apply them to a randomly permuted data set, and then the privacy guarantees for this result are upper bounded by the divergence by an arbitrary, and you can pick pretty much any divergence you like. We can look at the epsilon delta divergence of the differential privacy or other divergences, and we'll discuss those later. It's upper bounded by the divergence between the specific pair of distributions on 3 values. And we're on pairs of values, which is a trinomial distribution, in which the first element in the pair, actually in both pairs, the second element is C, where C is just the binomial distribution with n-1 elements, and the bias 1 over e to the epsilon 0, which is kind of the ones which choose in the crowd which choose to generate a clone. And the first element in the pair is either the Bernoulli with bias 1 over e to the epsilon plus 1, just as in the binary randomized response. And the second element is also binomial. Actually, that part is exactly the same as what we saw in the binary randomized response. Is just the sum of the Bernoulli and the binomial distribution with unbiased coin flip and the total number of flips being C. So just in the same way as we analyze the divergence for the binomial case with slightly different constants from the binary case, we'll get the analysis for the general case. So that's, as I mentioned, this applies to any divergence which is close to post-processing. Let me now just mention that sort of completes what I wanted to say about this result. Let me just mention a few new developments in this line of work that sort of are in the follow-up paper. So first of all, we actually give a tighter way to do this kind of cloning decomposition. And the key idea is that here we have been cloning the entire elements, the output of A on X1 and X prime, but we can effectively only clone the part where they behave differently. And that allows one to improve the constants in the analysis. Is again a little more subtle than what I'm saying here, but that's sort of the key difference. And just by doing that, here is the sort of the new numerical results, and maybe again in the same plot with maybe a little slightly different n. And now the orange line is the lower bound, and the green line just above it is the new bound, and the blue line is the bound we had before. They're a little bit easier to understand if one looks at the ratio between the upper and the between our bound and the lower bound. So yes. Did I hear a question? No.
I think there's no question. Thanks.
Okay, so this is the ratio of upper to lower bound. Is how far away are we? Our new upper bound is how far away it is from the optimum, and we can see that it's pretty much always below no more than 1.1, whereas the previous bound was worse by, again, like not that much, not that bad, but still was quite perceptibly worse.
Are both bounds, are they both asymptotically tight, or?
So yes, both. The new result also leads to an asymptotically tight bound. Effectively, it's actually strictly better than the bound, even like it's formally better than the bound we had before, which was already asymptotically tight.
Okay, I see.
So
yeah, do you have an idea of like the rate of convergence? Maybe it's not something you care about, because I guess you care more about like concrete values for like practical implementations.
So we care about both. We want to know, well, especially for theoretical analysis, we want to understand asymptotics. But for practical implementations and for practical analysis, we want to have tight bounds that we actually get as a result. And in fact, we only care about the numerical values in practice. So yes, but maybe a little more interesting. So then, okay, this is one new development. The other is actually related to the issue of composition. And in practice, we often need to analyze many more than just one algorithm, private algorithm. We just perform different analysis or many steps of the same analysis of the same algorithm, which means that we need to compose the privacy guarantees. And we know that differential privacy has composition results, but for epsilon delta privacy, this approximate differential privacy, the composition is doesn't work very well. It has also a variety of overheads. And specifically for this purpose, other notions of differential privacy have been more useful because they provide better composition. So maybe the most commonly used one and the one which gives the best typically used for composition is so-called Renyi differential privacy, which is parameterized by parameter alpha. And it specifically looks at instead of the epsilon delta way to measure the divergence between distributions using epsilon delta, it measures the divergence using the alpha Renyi divergence of order alpha, and that's here is the definition. It's just 1 over alpha minus 1 of natural logarithm of the expectation of the ratio of densities to the power alpha. And we say it's alpha rho Renyi differential private if the divergence is at most rho. So people have looked, maybe I should say that for this Renyi differential privacy, we prove asymptotically tight bound for the new development is an asymptotically tight bound, which specifically for order alpha Renyi differential privacy is on the order of alpha times e to the epsilon 0 divided by n. And here I'm focusing on the regime where epsilon 0 is larger than 1, because that's where the difference between all the previous new bounds and the previous bounds is. And we prove it for all alpha, which are up to n divided by e to the epsilon times whatever this bound that is stated. And this bound is kind of essentially all that matters. Otherwise, beyond this bound, the bound is not useful. Beyond this moment, the bound is not even useful because it becomes larger than epsilon 0, which is we always have just from the local differential privacy. And let me just briefly compare it what was previously known. So that first general result also gives a bound for Renyi differential privacy of alpha times e to the 6 epsilon 0 divided by n. So it's worse by this by a factor of 6, and has been improved by Gerges and others to e to the 2 epsilon divided by n, using basically in part our new cloning techniques, and in part some kind of explicit computations of Renyi differential privacy. It gives, again, it's not asymptotically not tight, and also it only applies for a relatively small range of alpha that is again stated there in the condition. So the proof of this asymptotic result is actually sort of one approach would be to just directly analyze the RDP of the divergence between these two explicit distributions that were described, but that's kind of tedious and we were maybe a little lazy. So instead we proved the general conversion from approximate differential privacy for a range of deltas where delta is larger or equal than some delta minimum to a guarantee on Renyi differential privacy, which holds for a range of alpha up to some parameter alpha. And that's sort of a tool that might be useful in other contexts. So that's all that I wanted to say about the newer paper, which hopefully will appear on arXiv soon. Okay, I guess we also have numerical evaluation for it. And here we're comparing the green is the lower bound, the orange, and sorry, maybe I should mention what we're measuring. We're measuring the Renyi divergent Renyi divergence for a specific value of epsilon 0 for a specific n, but we are looking at the value of Renyi divergence for different orders alpha. So the higher is alpha, so the higher is the moment. Higher moments are useful when you want to then argue about low probability events, like effectively very small delta. So again, the green is the lower, is numerically computed lower bound that one cannot improve on. This improved decomposition leads to orange bound. The one we had before we improved the decomposition is the blue line, a little worse by a constant. And the red line is the best, was the best numerical bound that I've mentioned before, which wasn't asymptotically tight. And since I mentioned that the motivation for this is for composition, is getting better composition results, here is how, this is how these results lead to better bounds for composition. And basically we're looking at the number of times we will compose this result, which is a t, and we'll look at the resulting epsilon as a result of composition. And we do composition. One way to do a composition is just apply our numerical results and compose them in as approximate, using the composition for approximate differential privacy. And the other way is to do a composition in the Renyi differential privacy. So this blue and orange lines are both of our Renyi differential privacy based bound, one, the previous one and the current one. And we compare it with the green one, which is just doing it epsilon delta dp. And the point is, as you can see, we get that going via Renyi differential privacy is very useful in this case.
I have a question about the x-axis. So the x-axis is the number of times you need to compose.
Yes.
So in this context, what does it mean when you need to compose it twice? Like, what's the scenario that I should think? I mean, like, you have n users and you shuffle them, but now what do you do if you have to compose twice?
Yeah, so there are different things. So for example, you could be doing something like gradient descent, which has lots of iterations. And for every iteration, you would be computing the gradient and getting some kind of bound via shuffling, and then you need to compose it with the bounds you get in the next iteration. So you would be applying some kind of shuffling for computation of every iteration. That's sort of the only case where I can think of as we would end up with like 1,000 iterations. Normally, you would probably have more like if you were to do simpler algorithms, like for example, building a histogram, would typically only require like depends. Most of the algorithms are of this type usually use no more than 10 iterations. So it's not as many, but we still get even for basically already for 2 iterations, we already improve. I mean, basically already for 2 iterations, the Renyi differential privacy improves on only using the approximate differential privacy bound. Does that answer your question, or?
Yes.
Okay, I also have a question.
Yes.
Does this work so what will happen if you directly compute the Renyi divergence between the two tuples, like the tuples you used in the previous proof?
Oh, right. You could, in principle, yeah, because these are explicit distributions, you could do an actual, try to do an RDP on those directly. It's my understanding that it shouldn't matter too much because they are still completely independent. Both the shufflings are independent and randomizers are independent. So now numerically it could, actually it could be better. I'm not too sure, but my sense that it's because of independence, it won't be a huge difference.
Okay, thank you.
Okay, so that's all that I had to say about the results. Let me just briefly conclude. So as I mentioned, the paper is online. It appeared in Fox 2021, and the follow-up will also be very soon on arXiv. There is also actually code if you want to do it. There is it's on GitHub. You can compute it. I mean, the code for numerical computations. And in the papers, you can find quite a bit more stuff. First of all, I mentioned that we have a more general version that can exploit additional structure in randomizers and then get better, and as a result, get better amplification. And we apply it for some specific k-randomized response mechanism. We have the generalization to epsilon 0 delta 0 local differentially private randomizers. And that one is useful, for example, if one adds Gaussian noise. Gaussian noise is does not satisfy pure differential privacy. It doesn't have, so we need to use this other version, and you can see the analysis in the paper. I mentioned that these kind of privacy amplification results can be used to improve given an analysis of the differentially private SGD. Previously, there wasn't all the analysis of typically differentially private SGD in theory was always analyzed for sampling with replacement, whereas in practice, differentially private SGD uses shuffling and not sampling with replacement. So we can now, using these new tools, we can analyze the actual, get asymptotically tight bound for analysis of actual DP SGD, although the bounds end up being a little worse. And there are some other applications to getting asymptotically tight frequency and distribution estimation in this shuffle model. When you shuffle, we show that you can recover the bounds that from the central model using shuffling for the problem of frequency estimation. And there are some additional numerical results as usual. Anyway, that's it. Please let me know if you have any questions.
Yeah, this is amazing work and a great talk as well.
I appreciate your comment. Thank you.
Yeah, I don't think there are any questions here in person. I don't see any on the chat here either. So I guess, yeah, we can thank Vitaly again. Yeah,
Sounds good to me. And thank you all for being a great audience.
Yeah, thanks for taking the time to give the talk. It's great. Thank you.
And let me know if you have any follow-up questions. I'm accessible emails or a quick chat online. Either way, feel free. Again, pleasure to meet you all today.
Thank you. You too.
Thank you.